Today, I want to talk about making great apps, both mobile apps and web apps, some of the problems that make that hard, and a few of the patterns and solutions that I think can really help us not only do that faster, but actually make more robust apps that use less complex code and that are actually easier to understand. A little bit about me. My name is Lee Byron. I work at Facebook on a team called Product Infrastructure. So product infrastructure, on this team, we build the technology and the tools that all of our products use to be the best that they can be. And part of that, I work on a lot of our open source technologies. So I'm a core contributor to React. I'm one of the co-creators of GraphQL, and I'm the creator and maintainer of Immutable.js. And I may mention these tools and a couple others just because they're relevant to how we're doing this at Facebook, but this talk is not about any specific library or framework. It's not actually about any specific platform or language either. What I want to talk about today is the architecture underneath the apps that we're all building. What I'm going to talk about applies just as much to an iOS app as it does to a JavaScript app. And these ideas can actually be implemented in a huge amount of ways. So what I'm going to show you is kind of one way to do this idea, but there's a lot of different forms that this can take. And in order to do this, I think it's really important that we first get a shared understanding of what it is we mean when we talk about architecture. When we're talking about software, architecture is a metaphor. And what we're actually doing is we're borrowing from the idea of building actual buildings. And there are some really clear parallels that we can draw between these ideas. Architecture itself originates from studying one of the most important technological advances in building things, and that's the arch. This very simple shape has proved to be nearly infinitely composable, which allows us to build larger and more complex buildings than ever before. This is Vitruvius. He was a Roman scholar and architect. And 2,000 years ago, he wrote about the principles for satisfying good architecture: firmitas, utilitas, and venustas. Firmitas means durability. A building should be robust and have longevity. And when we build apps, we look for the architectural choices that help us reduce bugs and improve performance. Utilitas means utility. A building should be relevant to how it's going to be used. You know, the materials, the technologies, and the aesthetics that you would choose to build your home are going to be very different from building an office building, or a place of worship, or an auditorium. It's because each of these places is used in a very different way. Similarly, the architectural choices that we make for our apps can differ wildly, depending on the complication of the app, how it's going to be used, if it's more static or dynamic, simple or complex, or if it's going to rely on more networked or live data. And venustas means beauty. Buildings should be both usable and desirable by using proportion, repetition, and scale. And obviously we want our apps to be desirable and usable, but what I believe the parallel here is not to user experience, but to developer experience. The architectural choices that we make, they impact not only how easy or hard it's going to be for our teams and ourselves to improve our apps, but to also iterate on those over time. So architecture is about making fundamental structural choices about how we're going to build things with the qualities that Vitruvius set out for us 2,000 years ago. In software architecture, we make these same fundamental structural choices based on our understanding of what our app needs to do and the challenges that it's going to face. We choose our few elements, our abstractions, to create variation and robustness to support the role of our app, solve its primary challenges, and create a productive space for ourselves and our other developers and engineers. And for the information-rich, user-facing apps like the web and mobile apps that a lot of us in the room have been building, there's been a really dominant architecture over the last decade or more, and that's MVC and REST. And for these kinds of apps, there's one single biggest challenge that we need to solve, and it's this: what changed? How can I tell when something has changed so that my models, my views, and my servers stay up to date with each other? And I believe that MVC has really just left us with a poor solution to this problem, because it attempts to solve this by adding even more things that can change. You've got models sending change events, views that are easy to get out of sync, and race conditions when you're doing multiple things interacting with the server. When models and views both need to listen to each other for changes, it's easy for what seems like what would be a small change to have these cascading effects that create unpredictable effects on your entire application. And there's also a second big challenge that these information-rich apps face, and that's synchronizing data with our servers. You know, modern mobile networks, they're just really crappy. Okay? First, there's latency. We can measure latency often in large parts of an entire second. So minimizing requests to our servers is actually really critical for performance. And then there's intermittency. So we often talk about supporting offline mode. But as we all know, no one goes offline. Instead, what happens is, you go underground on the metro, or you're driving in the car between cell towers. So what we're actually talking about when we say offline mode is intermittency mode. So handling these kinds of network failures is really critical. And while REST helped us model our data in terms of a networked service, it can really be crippling to performance when our app needs to load lots of data that's dependent on loading lots of other data. So let's take an example, okay? Say we want to build a social calendar app. We're going to need to get our friends. We're going to need to get their names and their profile pictures, their avatars. We want to know the next events that they're all attending and the names and the details of those events. And so we're going to have to load a lot of stuff from our REST endpoint. And since REST APIs typically return URLs when one resource references another resource, then we're going to end up loading lots of these things dependent on others. We're going to have to wait for previous URLs to load before we can even start loading the other ones. And that means that even the new stuff that we're getting, like HTTP2 pipelining, it just really can't help us solve this kind of problem. And when network latency on a mobile connection is measured in big chunks of a second, this stuff adds up really fast. You're talking about, for even moderately complicated apps, 3, 4, 5-second slowdowns just on the latency, not to mention all the other things that have to happen all over the network. So needing to deal with this problem of handling both a flaky network and a slow network, it puts us in a really sticky situation. We might want to show a loading indicator if someone performs an action in our apps, but networks can be slow, so we might not want to have them sit and stare at that loading indicator. We might just want to guess what the server's going to do and show that to them right away. But networks can be flaky, so what if that doesn't work? Are we going to roll it back? What happens if they've done multiple actions at the same time, and we've got to figure out what order to do these things in? It's a really big mess. And not only is this challenging, but it's also, unfortunately, a very common scenario that we need to solve in our apps. And so I actually think that there's a really powerful technique that we have to get a better control on these problems. And that's by tightly controlling what can change in the first place by embracing immutability. And what's really exciting about this to me is that immutability is not more complicated than what we've already been doing. It's actually less complicated because we're removing a feature. We're removing the ability to mutate data. And when we give up the ability to mutate data, we're giving up some power. We're giving up the power and the abilities that come with that power, but in exchange for that, we get new principles. And when we have principles, we have new guarantees about what can and can't happen in our programs, and we can leverage those principles, those guarantees, to do performance optimizations and other whole program optimizations to get a better app speed overall. And I really think this is the crux of what we do as software engineers. It's all about balancing between power and principles to get the power that we need to build the apps that we need to do, but also get the principles that we need in order to build the best things. And if we only cared about having our software have the most power possible, then we would have stopped at assembly or GoTo, right? Like, all languages are Turing complete, so we really have the same power everywhere. And GoTos are incredibly powerful. You can do a lot with them. But instead, we're always looking for more principled ways to apply the power that we already have. So of course, most modern languages, all modern languages, have forgone GoTo in favor of for loops. And you can't do everything with a for loop that you can do with GoTo, but the principles and the constraints that it provides let you guarantee some things about what can and can't happen in your app. And many of the more modern languages even forgo for loops in favor of map, filter, reduce, and other higher order functions that happen on things that you can loop over. So it's really not the power of your software, it's about the principles that you can leverage. And immutable data brings with it these principles, this guarantee about what can change and when, so that we can use techniques that previously we couldn't rely upon, like memoization and time travel. And I'll talk about those a little bit later. So I'm done with MVC and REST. I really think it's time to rethink the core architecture for how we build all the stuff that we build all the time. And as I've been observing the apps, both that we're building at Facebook and that I'm seeing built by the broader development community, I'm seeing a new kind of app architecture emerge to better solve these problems that I like to call the immutable app architecture. And it's heavily inspired by similar architectures that you've seen and may have seen in functional reactive programming environments, which has been the result of many years of research. So of course, these aren't all my ideas at all. And it's actually heavily inspired by the programming language Elm, which you'll hear about right after me when Jack presents. So immutable UI doesn't mean that our screen is frozen and you can't do anything with it. It's not like we're going back to 1998 web pages. Instead, what it means is that we're just going to embrace the principle of immutability at each point in the architecture of our application. That means that we're going to be able to control exactly where changes occurred, and then we're going to leverage that in order to apply some techniques like memoization and time travel to build faster, more robust apps. So let's start with first principles, views. Every platform that we care about building apps for already has a concept of a view. The web has DOM elements, iOS apps have UI views, Android has Android.view. But all of these have a similar API that helps you build this view tree, right? We want to use these because they expose the native user interface on each platform, but these APIs, they're not great. You create elements, you alter their properties, you add them to parent elements. All of these are mutative operations. We're talking about immutability. So, and after this, you got to keep track of all these references. And you do things like looking stuff up by ID and keeping things around as members in your classes. It's really hard to do this. There's just a lot of stuff that you got to keep track of. So what we really want is an abstraction on top of views that lets us declare what views should be displayed at any point in time. And we call these components. And a component, it just defines this pure function. Kind of the state of things, the state of the world goes in, and what you want to see on the screen comes out. And what a good component library should do for you is provide this pure functional developer API, but under the hood actually do all the hard work of managing this mutable view API that all of the platforms that we care about actually expose. And it needs to do that in a way that leverages all the performance techniques that we can get when we apply this limited power in favor of the principle of having this one function to define things. So let's take a closer look at this. Just an example. In my example, I'm going to call this my view, and it's going to have some data, okay? And when we render this component, what we're actually going to get back are virtual views. So virtual views are a representation of what we ultimately want to see, right? They have the same structure, elements, properties, children, but they're really just in-memory objects. They're not on screen yet. And what that lets us do is the first time we render these components and we get these views, our component library can take the virtual views and then create the actual underlying native views on whatever platform it is that we care about. And when our component function is called a second time, we provide some new data, then we're going to get a new set of virtual views. That's the output of calling that rendering function a second time. And so what our component library is going to do is compare virtual views from when it was previously called to now when it was just called, and it's going to compute a diff. And in computing a diff, what we're going to get is a translation into the set of mutable operations that we need to perform on the underlying native UI in order to get the views into the state that we want them to be in. So good component libraries can do this very, very efficiently, running really complicated apps at 60 frames per second, even on some mediocre mobile devices. So components are a really important aspect of this architecture, and of course React is an excellent library that implements this concept. React lets you write pure JavaScript functions and then manages the immutable DOM elements on the web page underneath for you. And if you're building native apps, you've got options. So there's React Native. React Native lets you write these component functions actually using the same React API in JavaScript, but actually will bridge down to the native UI framework, so it'll use UIKit on iOS, it'll use Android views on Android, it'll even use Windows UI views if you're building for Windows. But then there's also Component Kit. So Component Kit is this exact same idea, but it's entirely implemented in Objective-C. So if you're building iOS apps and you don't really want to deal with JavaScript, that's fine too. You can dive in here and you can write pure functions in Objective-C++, and it's going to manage the underlying UI views for you. And by the way, if you've ever used Facebook, hopefully you've used it once or twice, and you've used the news feed on an iOS app, you've used Component Kit in action. That's how all of our newsfeed product is built. So these component functions, they need some data as input, and that's where models are going to come in. But these are not the models that you may have seen in your favorite data management libraries before. These are immutable models, which means they're just pure data. They're very simple, accessors only, no setters, no events, nothing like that. And I really recommend building these with in JavaScript, just plain old objects, or whatever the equivalent of your plain old POJOs in Java. Or you can use persistent immutable data structures if you need to do something more complicated, like the ones that Immutable.js provides. And I'll talk a little bit about that in a moment. And then, of course, we need to get those models from our server. But I want to first take a closer look at these models and components together. So these two concepts are actually really tightly linked. They're coupled. When a component wants to render something new, right, you're building your app, you're adding a new feature, then you want to make sure that the corresponding model also is knowledgeable about whatever data you need for that new feature. That means that the server is also going to need to send that new data as well. Right? So we're going to add something to a render function. We've got to make sure that it's represented in our models as well. And since one model can appear in multiple views, and it's easy for these to end up in kind of different parts of your code base, it's really accidentally possible to kind of do something in your view and forget to put it in your model, and then you got broken UI. Or what I found is actually more common is that you're refactoring and you're kind of deleting some experiment that didn't work or something like that, and you forget to remove it from your model, and now you have overfetching. So if each component describes not just the function that you need to take the state of the world and give you your views, but also all the things that it will need from the model, then you have both of these things within the same place that define both what data you need and how to render that data onto the screen. Because they're described right next to each other, it's really easy to avoid these problems of overfetching, underfetching, broken UIs. And we call this co-located data dependencies. And at Facebook, we do this using a tool called GraphQL, which if you're here for the backend, you might have already heard a little bit about. But if you haven't, GraphQL is an API query language that we've developed at Facebook as a replacement for REST. And it powers all of our mobile apps at Facebook. And if you haven't seen GraphQL, I'll just give you a brief overview of what it feels like to use GraphQL. So this is kind of the hello world of GraphQL queries. I just want to get my name. And the first thing you'll notice is that this looks a little bit like JSON. We've got these curly braces. They look a little bit like objects. We've got these things here that look a little bit like object keys. We call those fields. And if we send this query to our GraphQL server, it's going to resolve and come back as a JSON body. And one thing you'll probably notice here is that this JSON body and the query have very similar structure. And this is an important part of what makes GraphQL easy to learn and use. And it also provides some principles that lets us do some really interesting optimizations with GraphQL in sophisticated systems. And we can also request fields of complicated data. So here, there's a profile picture, an avatar, and it's got not just a URL to go load, but also the width and height, so we can make sure we get the right region of the screen before that URL comes back. And I bet you can already guess what this looks like if we run this, right? It's going to look exactly like the query. But more importantly, GraphQL is designed not just to query stuff about one resource. It's designed to smoothly navigate between resources in a single query. So for example, I can get not just my name, but the names of all of my friends, and do that in a single query. And notice that here's where a REST API would have given us a list of URLs to go load a second time. Or maybe you've got a sophisticated REST library that lets you pass some additional fields that you want to do and get these names instead of URLs. But it's a little bit harder to do that at multiple levels down, and GraphQL makes that really easy. So remember our example from before where we were making a social calendar? Well, this is all the data that we need to render that social calendar. We've got our name, we've got our friends, we've got our events, right? And we can do that in a single round trip. Huge difference, dramatically improving our network performance. And in order to match how developers, how they think about views, and to allow for portions of queries to be recycled, GraphQL has this language feature called fragments. And what fragments let us do is describe co-located data dependencies right next to our components. And so here we have a component that describes both the data that we need and the rendering function to do a profile picture on Facebook. So we need a profile picture of our user, we need the width, height, and URI, and then we're going to render an image tag. And what we can do is we can use that component within another component. So here we're rendering, maybe a row and a list of users. We want to know the name of the user. We want to know if they're friends with them or not, so we can render this button. And then we want to render this profile pic. So of course we're going to need the name and the are you friends. But for profile pic, it's a little bit cumbersome to repeat that data. So instead what we do is we just reference this other fragment. And then we get all the data that we need, no more, no less. And query fragments, they let us define not just the requirements next to one component and compose them one time, but they compose all the way for your entire app. So you can have a really complicated application, which has tons of nested views, and then you can describe all those things and roll them up into a single query that we can run in one round trip to the network and get all the data exactly as you need it, no more, no less, to render your app, which is huge for network performance, also for understandability. OK, so what we have so far is great for like a read-only app, like maybe a news reader or something like that. But what about apps where we have actions? We have stuff where a user is going to interact with our views. We need to perform actions. And we have these models that are immutable, so we're going to need one place where we can apply those changes. We're going to call that state. It's really just like a bucket where we can hold on to all of our models. So we also have the initial query to our server. That's going to give us kind of our initial state. And of course, we want state to also be immutable, so we can't change that thing. So what exactly is happening here? Well, let's look at an action. An action is just a function. It takes the old state of the world in, and it returns the new state of the world. So you might write an action that takes in the old state of the world, and then makes some changes to some models, applies whatever change you want, and returns a new version of the state with that change applied. And once this action returns a new state with some new models, then we can provide those to your components, which are going to go back to your views, which are going to then update the underlying native views. Those then you can act on, and we can then get back to our state again. So it's a loop. And so you might be thinking, OK, that's fine, but like these functions that change your whole state, you're going to do that for every time the user does anything. That's going to be really slow, right? Well, actually not really, and not really because we can leverage the principle of immutability to do this really cool thing called structural sharing. So what structural sharing lets us do is take a previous version of some immutable thing and some change we want to apply, and then recycle as much of the old version of that thing as possible, literally all the underlying memory we want to recycle if we can. We can do this for plain objects, but this actually enables an entire class of really interesting data structures called persistent immutable data structures. I'll just illustrate a little bit how this is going to work. And by the way, if this is interesting to you and you're a JavaScript person, you can check out Immutable.js, which is just an implementation of these data structures. So let's take a look at this example here. There's some structure of data, and we want to make this change. So in order to make this change, we can't do it in place, so we kind of have to copy this node with a change applied. And it can reference other nodes, that's fine. But anything that points to it also needs to change in order to have that new pointer. Again, no mutation, so we copy that thing. And we do that all the way until we get to kind of the top of our data structure. And once we do that, then we have a completely new structure with our change applied. And importantly, we've recycled a lot of this. This is super contrived. I just got it to fit on the screen, but it still recycles more than 50% of what's happening here. And in practice, it's more like in the 90+ percentile. Most importantly, we haven't changed anything about the existing data structure. We can use this continuously That's totally fine. We can actually use both of these at the same time if we want to. That'll continue to work. And as soon as we don't want the old one anymore, we can just let go of it, and the garbage collector will handle that for us. And any modern JavaScript VM or Java VM or anything like that with a good garbage collector, this stuff is super performant. It's not going to be a problem. And so by doing this, we can really leverage immutability while still having very good performance for CPU and memory. And a prime example of the kinds of things that we can do when we have this is memoization. So memoization is when you take a function and if you call it a second time with the same arguments, you want to kind of skip running the function and just return whatever it returned last time. So this is a cool performance technique that you can do for expensive functions like rendering a UI. And so I want to show like a really basic example. This is going to be the sum function. So we're going to take a list of numbers. We're going to add them all up. And I know I'm going to give this like a really big list of numbers, so I want to memoize it. So I'm going to give a list from 1 to 1,000,000, and then I'm going to add them all up, and then I'm going to push onto that array and then call this again. So this is what I want to see, right? So I went looking for this function. I literally went on Stack Overflow, and it was like JavaScript memoize. And it was like, here's the most uprated version of memoize. And I simplified it a little bit just to get it to fit on the screen, but this is largely it. And I don't know if you guys see the problem with this, but it's this, JSON stringify. Of course, we're doing memoization to get better performance, but JSON stringify is really expensive, especially if the input is big, which is exactly why we're doing this. And so, as you might expect, running the memoized version of this is actually much slower than running the not memoized version. Totally not what we want to see happen. So I rewrote the function. And instead of using JSON stringify, I just want to see if these two things are equal. That's all. So I did this. So I ran it. And at first, it looked really good, right? I called it a second time, and it looked like it was basically free. And then I pushed my next number, and I called this again. But this time, it didn't do what I expected. It looks like it memoized, and it didn't return the right answer. Of course, this is why an array is mutable. When you push into it, you don't change the identity of that array. It's still equal to itself, so this check passes, and got it. Now I understand why JSON stringify was there. But let's try that same thing and use immutable list from Immutable.js. So same exact implementation of memoize. I haven't changed anything. I've just replaced arrays with lists. Immutable lists. So far, so good. This basically works the same. And if you're paying really close attention, you might notice that calling sum on a list rather than array is a little bit slower. That's to be expected. Immutable data structures are a little bit slower than their mutable cousins. But what we want to do is reap that performance benefit back by applying these global optimizations. And now I'm going to push into it. What will happen with an immutable data structure is when you push into it, rather than changing that thing, it's just going to return a new version of itself. So we're going to make sure that we keep track of that. And then we get the answer that we want. So this is great. So back to our diagram. We're missing a big important piece. And that's how our actions are going to communicate with our server, doing that synchronization. So let's go back and look at what an action is. An action is this function that takes the old world and returns the new world, right? But if we're going to go to our servers, this isn't going to cut it. We need asynchronicity. We need to be able to wait for the server to get back to us. So what we really want is like a promise or a task that will eventually give us back our new state. But like we talked about, this could be slow. We don't want to be slow. We want to show people updated UI as quickly as possible. And even on a really fast network connection, even if you're on a desktop computer and you've got like a hard line, people are really good at noticing delays. Like we notice delays in hundredths of a second. So even on a fast network connection, it's noticeable. But of course, on a more typical, slow mobile connection, it's going to be just really painful. So here's actually what we want to do. We want to return immediately our guess at what we think the new version of the state is going to be, which we can do locally. But we also want to return a promise for the real version of the new version of the world that the server is going to help us fulfill. And that brings me to one last problem, and that's what do we do when there's multiple actions happening at the same time? And for this, we need a queue. So this is the last important part of this architecture, and it's going to make sure that things happen in the right order and we don't get race conditions. So a queue, what it's going to do is going to keep track of the most recent version of the true state, what our server thinks is true, and then it's going to keep a list of the options or the actions that are currently in flight. So say a new action comes in, what we're going to do is immediately compute what we think the state is going to be. We call that our optimistic state. And then we send this to the server. And if a new action comes in, that's fine. We just add it to the queue, and we compute a new optimistic state. And then when the first one is done, that's great. We can just remove it from the queue. We're going to get a new version of our true state from our server from having done that, and we'll just recompute the optimistic state if there's anything left in our actions queue. And then when that second one comes back, then we're dealing with true data again. Nothing new to apply. We just have true state, optimistic state, same thing. So this is really interesting because it lets us model apps that let us first create a thing, like a to-do item. Wouldn't be complete without like a to-do app example here. And then lets us kind of make changes to that thing even before the server knows that it exists. And this is usually something that's hard to do. So first we're going to create a to-do, and then we're going to change some stuff about that. And at this point, we don't really know how to tell the server, hey, set the due date of this to-do item that we don't know anything about yet. So we got to wait for the server to come back and say, well, here's the unique ID for that to-do, and then we can replay that action to get a new optimistic state. And once that has been done, then we can actually have the information we need to go to the server and give it the right info to do that thing, and then we have the state of the world that we want. So this kind of behavior, it's typically really hard to do in traditional apps. You may have bumped into this before. I do kind of all the time. And it's really hard to do without creating race conditions. And so this technique lets us avoid the majority of the race conditions that we end up running into. All right, let's take one last look at this whole architecture. Our components describe the data that they need, which informs the shape of our plain old object immutable models, which are first created as the result of a structured query that we send to our servers, which creates our app's initial state. From there, these models are provided to our components function, which is going to describe our views, which are then actually created in the underlying UI view framework. And then we're going to interact with those views, which is going to create actions. Those actions are going to optimistically update our states, but they're also going to be added to that queue and asynchronously sent to the server to let them know about that change. And when the server responds, then we're going to get the action removed from the queue, applied to get an updated version of the state, which is going to contain new models. We're going to provide that again to our component rendering function, which is going to describe new views, which will then take the underlying native views and update them as efficiently as possible. And then we're going to repeat that forever and ever and ever and ever until the user leaves your app, kind of depending on how good your growth team is. So this, I think, makes some dramatic progress on solving the challenges that we have in the modern apps that we're building today. It lets us keep track of what's changed, keeping our UI up to date, synchronizing with the server that more and more recently is at the end of a slow, spotty network connection. And we can do all this precisely because everything is immutable. If part of our code base, any part of our code base, could edit our models or our views at any point in time, which is super common in MVC frameworks, then we couldn't use any of these techniques anymore. We would have given up principles in favor of power. We couldn't apply actions in order. We couldn't easily roll back state. We couldn't do these optimized view recycling techniques. And we couldn't do all this on multi-threaded platforms like iOS and Android, where a mutation makes jumping between threads very difficult. And also this architecture, it's simpler than MVC and REST because there's no direct mutation. So I know I've covered a lot of pieces here, and it feels complicated. And of course, component libraries are very sophisticated. And they can be that way because they're leveraging these simple principles: pure functions, immutability, and composition. And what makes me really excited about this is that this powers a lot of our apps at Facebook, where most of our mobile apps actually follow this pattern. I mentioned earlier that if you use Newsfeed, you're using some of this stuff. Newsfeed was actually one of the inspirations for putting this talk together. So I really think that traditional MVC and languages that have mutation by default are going to slowly be added to the pile of old ideas. But I'll leave you with this. MVC and REST, they did not solve all of the problems that we face in app development. But what I've presented today also won't. Right? These ideas are going to be far from flawless, and they might not be right for the app that you're building. And I want all of us to continue to challenge the notion that there's like one right way to do things. That's not true. And also just recognize how quickly and continuously our ideas about what good architecture is and good technology ideas are. Just every time I finish building something, I just have this urge to go back to the beginning and start over because, of course, by the very nature of having built it, I've seen all the things that went wrong, and I want to do it again with all the ideas that I have to make it better. But of course, if I did that, as soon as I was done, I'd want to do it again because I would have seen even more ways to do it better. And so for just this reason, I think it's, the process of this architectural improvement, it's just never ending. It'll never end. And we're never going to end up at like an architecture nirvana where we have all the answers. It's just not going to happen. It's an important realization. And what fuels me is this process of exploration and trying new things. It's the process of improvement that's exciting, rather than some mythical, destination of perfection in our apps. So I hope that you found these ideas of immutable app architecture interesting. Hopefully they're useful for some of the things that you're building today. But more importantly, I hope that it inspires you to continue to improve on these ideas so that we can all build even better apps tomorrow. So thank you.